All right, welcome to Physics 20. This is where we begin at lesson 0. And what we're going to do in lesson 0 is just recap some basic skills that will be very fundamental for us going forward in terms of answering questions, completing labs, or just the overall formatting of answers that we would look for, which the main topic included here is significant digits, and you'll see what that means very shortly. So let's begin off with the first slide here and looking at scientific notation. Scientific notation is composed of two parts. The two parts that make up scientific notation, namely A and B, which is this top part here, we'll start off with A and say, well, A is representative of the base. Now, the base value, we want to be really specific, and this is going to range from 1 to all the way up to 10. Now, a prime example of this might be something like, what if I give the example of something like 2.3 times 10 to the fourth power? Not that it really matters. We would look at this and say that this constitutes the base, the 2.3. The exponent part, that's a totally different piece. And the times 10 to, we don't want to worry about that. We just want to worry about this base value. And we see that that is a number that ranges between 1 and 10, where it is exclusively less than 10. Now, when we talk about B, what is B? B is the exponent. And so the exponent value, the only thing we want to include about this is not only its official title of being the exponent, but we also want to say that it could either be positive or negative. Positive being larger numbers. So if I take a really large number and I truncate it, I would have a positive B value or a positive exponent here. So this would be positive. And if I have a negative, this means it was some sort of smaller number. And so I'll make sure to put the hashtag next to these just to indicate that it is talking about number. And so a negative number or a negative in the place of B would indicate that this is going to be some small number that we're trying to move into scientific notation or truncate. Now, really important, this is what you want to highlight. Only the base is included in determining the number of significant figures, meaning when we look to do significant digits, we're only going to look at the A value or this base value, the piece that's out in front of the number. So for the example that we generated here, we would say that this has 2 significant digits. Okay, now continuing forward, what we're going to do is work with some scientific notation and either expand numbers or collapse them down into scientific notation, keeping a certain amount of decimal places. So the first one, we see a positive exponent. This is to the power of 4. Power of 4 means because it's positive, this is representative of a larger number. Now, not only is this a larger number, but what the 4 indicates or what the exponent indicates is how many spots we're going to move this decimal to the right-hand side. And so I see this and I see, well, to the power of 4, it's going to move 4 spots. And so my number is going to be 401. And then if I add another 2 zeros to make this a complete 4-digit move or a 4 decimal place move, that should be my number. So 40,100. Now, again, we see a positive exponent to the power of 2. This case, it's only going to move 2 spots to the right, but it is still moving to the right because it's positive. So I'm going to make this number 702.9. And we can make this 90. We can make this 90000 if we really wanted to. They didn't give us a restriction on the number. I'm just keeping it to 4 because that's how the number was originally. Now, in the case of this next one, we see to the -5, you got to remember that negative in the exponent indicates that this was a small number that got truncated into the scientific notation. And so when we see the negative, we're instead going to move this decimal spot 5 units to the left or 5 spots to the left. And so this is going to form the following number, 0.0005193. So it's a quite small number. It's something past the 1,000th decimal place, so this is very small overall. And again, we see that -5. This should indicate that we're moving 5 spots to the left. Now, on the contrast, or on the opposite spectrum of this, we look at this and we say, well, rather than dealing with scientific notation originally, what if we deal with a number that is just in its expanded form and we want to bring it down into its scientific notation representation? Well, in this case, what we're going to do is we're going to keep 2 decimal places according to the restriction here. And more importantly, the base is going to have 2 digits. So in this first case, well, where I would put the decimal spot right here. And in order to move this into scientific notation, where the value of the base is between 1 and 10 exclusively, and we only have 2 decimal places, I'm going to move this 1, 2, 3, 4, 5 spots, and the number is going to become 4.0. I'm going to round this because it's 0.5. I'm going to round it to 4.01 times 10 to the power of 5. Okay, now in the next number, instead we have a really small number. We're going to move the decimal spot from way over here to somewhere over on the right-hand side here. Let's count how many spots. So it's 1, 2, 3, 4, 5, 6, 7, 8 spots. And because I want to have this to 2 decimal places, I'm going to write it as 3.00 times 10 to the negative 8. Because remember, we're moving this thing a really small number and making it into the scientific notation, meaning we had to take this and move it a certain amount of spots right. Okay, lastly, we look at this example here. We have a really large number, so if I was to predict what the exponent should be, it's definitely going to be positive, but let's see how many times we have to move it. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. And so what I'm going to do is write this as 6 point. Now I have to realize that it's 6186. I only want 3 of these digits, so it's going to be 6.19 times 10 to the negative 9. Because we want to do a little bit of rounding there. Okay, perfect. So now, not only have we expanded numbers from scientific notation, we've taken numbers that were expanded and put them into scientific notation. And then just a quick correction here. I know I just put a negative there. We want to make sure this is a positive 9 because we took a really large number and put it into scientific notation. So just make sure that you go back and look at this, make sure it's positive. All right, now you're probably wondering, why are we doing all this scientific notation stuff? Why are we considering sig figs or significant digits? Well, the reason is purely accuracy. We just want to make sure that we have the most accurate reporting in our numbers and the most universal answer. So there may be times where we say, hey, we want to round it to a certain decimal place, and that will either indicate, hey, we're trying to aim for a certain accuracy, or we're trying to communicate an answer that is universal to everybody else's answers. So a prime example might be, hey, we're doing something involving acceleration or something involving a speed, and rather than having this infinite decimal place where it's an irrational number, we may say, hey, let's round it to something like a number like, for example, let's go 2.13 or something like 6.26. Both of these are rounded to the nearest hundredth, and so we would look at these and say that's the level of accuracy we're looking for, is just something that is to 2 decimal places, but realistically I could ask for 4 decimal places, 5 decimal places. It really depends on what the problem gives you as well. That also indicates how many significant digits matter or what digits matter in the overall problem. So let's look a little bit more into this closely. So on the next slide here, we're going to look at this and say, well, all digits from 1 to 9 and zeros in the middle of a number are measured to be significant. So in the first example, we look at this and we see 1667. Well, I count the total digits there and I would go, there is 4 significant digits. In the next one, there's a 0 in the middle, but that's okay. We're going to look at this and say there is 3 significant digits. In the next one, remember, if you need to highlight this for yourself, we see that the base value determines the significant digits. There is 3 total significant digits. And then in the fourth example, we just see a number where there's a bunch of zeros in the middle, 2 digits on the outside. This is 5 significant digits. Okay, pretty straightforward. Now we go on to a next example here, but we create a restriction around, or one of the digit rules, if we want to implement it that way, where we talk about leading zeros and how they're not significant. Leading zeros simply mean if I see a number that is a 0 out front of any sort of string of digits, just like we see in all of these examples, we almost want to X them out. So what I'm going to do, and what I did in class, is we just took these and we just crossed them out. We put an X through them and said, we don't even want to consider these. These are all just garbage to us. We look at those and say, they have no bearing on how many significant digits they are. These leading zeros are not significant. So in the first example, we have 3 significant digits, ignoring the zeros. We have 4 in the next example. And remember, zeros in the middle are totally fine. They just can't be out in front. We have 3 in the third example. And lastly, we have 2 in the final example here. So just make sure your leading zeros, don't look at them. They are not significant. They are not considered to be significant digits. Now, another rule we look at is the trailing zeros. Trailing zeros are significant. So if you see like numbers 1 through 9 out in front, and then you see a bunch of zeros that come after that, well, they're still considered significant. So in the first example, I say there's 4. In this one, what I'm going to do is cancel out the leading zero and then look at the trailing zeros or the middle zeros and consider them to be significant digits, meaning there is also 4 in this one. Again, I'm going to cancel out the zeros on the front because I don't want to consider the leading zeros. I see that I have 3 significant digits. And then lastly, there's no leading zeros, but there's some zeros in the middle or trailing zeros. Both of those count. And so I'm going to say that this is 4 significant digits. Because again, when we look at terms in scientific notation, we only look at the base, and that's it to determine the significant digits. All right, now, an important rule around conversion factors and countable figures. If we have any sort of conversion factor, so a certain amount of meters to a kilometer or a certain amount of millimeters to a centimeter, whatever it might be, we consider these to have infinite significant digits. Similarly, if we do with countable things, we always consider these to be infinite. Now, would I worry necessarily about these throughout the year in terms of almost being distractors for you? Not really, but you just need to be aware that the further you go, you have to look at these things and say infinite. And there's a really big reason we say these are infinite, and it's to avoid the distraction of treating these as something to count in terms of what we should be rounding things to. Because when we look at throughout the problem, we want to actually use the context clues in terms of speeds given or distances given as the way to direct how many significant digits, and not treat things like conversion factors or countable figures as something that might contribute to that. Because realistically, countable figures are just a stat of what might be happening in the context of what the problem is. And then conversion factors are just known values. So we don't want to treat a known value like it has any bearing on specific data within a problem. So let's see what that maybe looks like in the future. That might come up within lesson 1, 2, and 3. But for now, just treat it as these things are going to be considered infinite. All right, now something that's really important, most important rule of the year. If you want to put stars next to this, if you want to really highlight this for yourself, this is our most important rule, and this is how we're going to treat significant digits throughout the entire semester here. When multiplying or dividing numbers, the answer that we get will always involve the fewest number of significant digits we see. And so what that means is between the terms given, you're going to analyze it and be like, which of the numbers has the fewest significant digits, and that will determine how I answer this problem. So in the case of the first one, we look at this and we were like, okay, well, I scan it, and I'm like, okay, between those two numbers, we have, in the first case, 5 significant digits, and then we have 3 significant digits. So therefore, what should our answer have? It should only have 3, and therefore, when we calculate this, when we multiply the two numbers, we get 263 is my answer. In the next example, well, we have 4 and 4, so our final answer is going to have 4, and so I'm going to write it as 0.4035. Now, the interesting thing about this is you could write it in terms of scientific notation. You move the decimal spot 1 to the right, and you can get 4.035 times 10 to the negative 1. I've moved it 1 spot to my right, and therefore it's a small number that's getting put into scientific notation. It should have a negative. In terms of the next one, remember, we always look at the base. So we have 2 significant digits and 3 significant digits. And so therefore my answer is only going to have 2. I'm going to write this as 7.5 times 10 to the power of 11. There we go. And then lastly, we see 4 significant digits in this one and 3 significant digits in this one. And when I multiply these two numbers together, I actually get 25.3. So between the terms, or whatever terms you're given, or whatever key information you're given in the problem, just look through it and say, how many significant digits are there? Whatever the fewest amount, that determines how I answer the problem. And I want you to use this method all the way through this semester. Really, really important. All right, now this is a secondary rule, so I wouldn't really necessarily star it. I wouldn't really necessarily put too much attention into it, but if you're only adding and subtracting, particularly only adding and subtracting, you will look for the number that has the fewest number of decimal places. So what this means is it says, well, suppose I add the two following numbers in the first example. Well, we look at this and say, there is 3 decimal places here, and there is 1 decimal places there. So between the two numbers, the one that has the fewest decimal places is the second number. And so when I add these two things together, I get 188.8. I'm only going to put the 1 decimal. Similarly, in the next example, we see that both of these numbers, 133, are whole numbers. They include no decimals, so I shouldn't have any sort of decimal in my answer. And in fact, when I subtract these, I just get 67. In the next example, I see that I have, with this first one, 1. With the second one, I have 3 decimal places, so therefore my answer should only have 1 decimal place. You subtract them, you get 2110.4 or 2110.4. Okay, in the next example, remember we only look at the base value. This has 1, this has 2. So I'm going to put that underneath these. This has 1 decimal, this has 2 decimals. So when I not multiply, but when I add these together, I get the following number. This is going to be equal to 2.7 times 10 to the 6. And just remember, anytime you have 10 to the 6, I want you to kind of keep this backtracked in your mind. Not that it's super important, but anything 10 to the 6, it means it's a million. Anything 10 to the 5 means it's in the 100,000s. And then obviously as you trickle down, you get to smaller numbers, but 10 to the 6 always represents the millions. Now, between these, again, when I look at this slide versus the last slide, this is the rule we're going to be dealing with. So I really want you to key in on the multiplication and slash division where we take the fewest number available of the significant digits and that determines it rather than thinking about in terms of decimal places. You may be asked to do this. You may be asked to do this within the practice problems, but the first rule or the one that's on this slide is more important. All right, now a little bit about graphing. This is really key. When we graph, there's going to be a couple key components I'm looking for. Namely, I'm always going to look for you to title your graph, and I'm always going to look for you to label and properly do your 2 axes. So label and scale the X and Y axes. Now, going with that point, or going with a part of number 2, we always want to look at it and say, our first column of data should always represent the manipulated or independent. And in physics, what we're going to see is that this often is the time. So you could even put that right next to there and just say, often time is going to be our independent, and it's very rare that we would swap that, especially for the most of the labs we're going to do, time is always going to be on our independent axis or the x-axis. Secondly, we look at this and say, well, I see in the second column, we should always see the responding variable. In our case, the responding variable could be distance, displacement, speed, velocity, acceleration. It's probably going to be one of those things, but it's always going to be something where after a certain amount of time or after we input a certain amount of time, a certain result becomes the output, and it's one of those key things. So when we get to lab 1, just be aware that I'm looking for all of these things. And if you don't include things like a title or properly labeled axes, you're going to get marks taken off. And the really good place to practice this is in the lesson 0 section right at the end. So lesson 0, if you go to the practice booklet, you're going to see an example of graphing that you can do to make sure you know this skill. All right. Now, another point in graphing, and this is huge. When we talk about lab 1, 2, and 3, you're going to have to do this skill. The skill is line of best fit, which is super critical. And if you haven't heard of this, it's a good time to know about it. Line of best fit essentially just says, if I take a bunch of data that I've been given throughout the problem or I discover throughout the experiment or lab, what I'm going to do is I'm going to plot all that information, which looks like the black dots on these graphs. Then what I'm going to do is I'm going to draw a line through it, not connecting the points, but drawing an approximation of the average of those points. And so a line of best fit, when we look at this, it does not have to go through the origin 0, 0, but can go through that. So we look at this, and that is a really critical piece here, is that in these examples, they go through the origin. So we would say that's okay for these 2 specific answers, and that might mean something for the context. But if it doesn't go through the origin and the overall approximation is still there, perfect, excellent. Now, here's a massive point as well. Don't join the points. We mentioned that. The one thing you really can't skip over on this slide is the following. When we're finding the slope of these lines or slope of this line of best fit, do not use the plotted points. What that means is essentially, if you're looking down this, you wouldn't use these black points here, the ones that we were from the experiment. What you're going to want to do, and this is what we're going to do on the next slide here, is you're going to want to pick definite points. And what I typically mean by that is, if you look, this definitely crosses through a given point. This definitely crosses through a given point, and it's very easily readable off the graph. And so you'd put a dot here, you calculate the slope. Very similarly, you could go over here and say, okay, this is a definite point, and this is a definite point, and so I could figure out, well, in a curved line, you'd want to figure out the tangencies or the slope of the tangent line. So that's a different topic in and of itself, but you really want to pick points that are directly on the curve that you drew or directly on the line of best fit rather than picking points that were data points from your experiment. All right, so finding the slope, let's use that skill that I just mentioned right away. We're gonna pick some definite points. Here's one, here's one. Now, what I'm gonna do is I'm gonna put the ordered pairs. So this one is gonna be 14 and 50, 50 being the output, input being the 14 seconds. Our second one here, which is the one down here, is gonna be at a time of 7, so that's our input. Our output is 25. Now, when we calculate the slope off to the side here, we're gonna say that m is equal to the first y value, or y2, minus y1, which is 25, divided by, we take 14 minus 7. Now, this is going to give us a slope. M is equal to 25 divided by 7. And in your calculator, if you do this, what you're going to find is that this is equal to 3.6. Now, here's a super important piece of this, is that we've totally just overlooked this, and you don't want to do this on a lab. When we do this, we want to actually include the units alongside of this. 25 was the difference in the given height, or the difference in the output, meaning it was the meters involved. And then when we looked at the, in this case, the run, because it's rise over run to calculate the slope, this 7 is representative of the seconds. And so when we put this together, we say that the slope of this graph gave us 3.6 meters per second. So when we talk about a jogger's position versus time, when we calculate the slope, it's actually talking about the jogger's speed, which is really critical. And so we get speed out of this marker here. All right. Now, last example, which is doing some unit analysis and making sure we're able to do this unit analysis skill, because it's a huge piece of this. So when we do the unit analysis, let's just be a little bit aware here. So in the first example, here's what we're going to do. I'm going to set up the ratio where we say our answer, 120 meters, multiplied by, to do unit analysis, we're going to take known conversion factors and allow us to cancel out units that we were given so that we can go to units that we want. In 1 kilometer, there is 1,000 meters. And the reason I write it this way is because if I have meters in the numerator and denominator, those things can cancel out right away. When I divide this, 120 divided by 1,000, that's like moving the decimal spot 3 times. I'm going to get 0.120 kilometers. So there's my answer right there, is we can get our kilometers just by doing a simple unit analysis or taking a known conversion factor and using unit analysis to eliminate it. Now, let's do that same skill, but we need to cancel out 2 units and convert them into new units. So we're going from meters per second into kilometers per hour. So right away, what I'm going to do is I'm going to go 35.2 meters per second, and I'm going to write it in a fraction like this, multiplied by, we need to do 2 different sections here. So the first one being, let's say I wanted to take the meters and convert them to kilometers. Well, we knew from the previous section, 1,000 meters is equal to 1 kilometer. That's our first conversion factor. The second conversion factor is going to be the following. We want to get rid of the seconds. Well, in 1 hour, there's 3,600 seconds. So we're going to write 1 hour divided by 3,600 seconds divided by 1 hour. Now, when we go down the line and cancel out our units, meters cancel, seconds cancel, and hey, look, we have that kilometers over an hour like we're looking for. Now, we can do the math of this, and so if we do the full math around this, we would say that this is equal to, and if you hold on just for a second, I can type this in, we're going to do 35.2 multiplied by 3.6, because 3,600 over 1,000 is 3.6, so 3.6 times 35.2, we get 126.72, but what I want to be aware of with this is that this is in kilometers per hour, so that's perfect, but we also want to account for the significant digits. There is only 3 sig digs here, and so what I want to round my answer to is 127 kilometers per hour. Now, here's something that I highly recommend you write down, and I'm going to put it in a note right below. If we want to go from meters per second into kilometers per hour, so I'm going to write it like this, meters per second into kilometers per hour. There is a simple conversion we can remember. With this one, and I'm going to put the HR, there we go. There's a simple conversion we do. Meters per second into kilometers per hour, we're going to multiply the answer by 3.6. So that's our simple remembrance rule here. And that's exactly what we did in the unit analysis, just in a short form. So meters per second into kilometers per hour, we multiply by 3.6. On the opposite case, if I want to go from kilometers per hour into meters per second, what I'm going to do is I'm going to divide by 3.6. So the nice easy rule about this is it's always going to be 3.6, but then whether you multiply or you divide, that's going to be the big difference maker. Now, I can't stress how important this line is. This simple rule is going to be very critical, especially when you go to do exams, or you go to do any sort of unit test or quiz. Oftentimes, what we might do is we say, hey, I'm going to give you something in meters or kilometers or whatever it might be. And then maybe your answer is expected in another unit. And so you're going to have to be able to quickly exchange between backwards and forwards. The one that I'll say appears a lot throughout our tests and exams is the following: kilometers per hour given in the unit or in the line of the actual question, and then when they actually want the final solution, they want it in meters per second. That's very common, and it's one of those things just to like kind of keep your mind going. And rather than just being plugging and chugging answers, you have to critically think and say, do they want things in kilometers per hour, or do they want something in another unit? And so just be very aware of that. And I would get some work with doing the short form and potentially doing the unit analysis because of how critical it is in the other sciences. Okay, that does it for lesson 0. Please go get some practice. Do all the practice problems for lesson 0. It's critical you get all of that information and you're able to replicate all the stuff we talked about here on your own for your own practice problems.